Thank you, Rodrigo. Thank you, Luis. Good morning to you all. Yes, it's almost midnight here. Hopefully, I will be able to finish before sleeping. Okay. Yeah, the title of my talk is a wide bandgap devices in power systems. Just before starting the topics, I would like to just, if you are not familiar to the Australia, I'm in South Australia. South Australia is if you consider the Australia, is the middle south section, which is relatively isolated. Isolated means really in Australia, the transmission line is also very long and thin, almost around the coastline. South Australia is nearest Melbourne, for instance, Victoria is about 700 kilometers away. We have transmission lines, but very also weak and then thin. The reason I'm giving you this background is that we started about 10 years ago, the renewable energy integration became a very, very strong. And now South Australia, probably after Denmark, probably second, sometimes also first in the world in terms of renewable energy integration. Our daily, even some instant level, renewable energy penetration mainly from wind and then solar, PV, rooftop primarily, sometimes almost 100%. And then PV integration is still increasing. What we had is, in fact, I probably summarize in this first slide. Therefore, we are experiencing the power system transformation probably much earlier than any other places in the world. We have also, as a part of these activities, we experience various difficulties because of that long, thin, and weak structure. The stability issues are very pronounced. And we had also very big blackout to around 2016, September, October timeframe. Then since then, PV penetration, renewable penetration is still increasing. And then plus South Australia also has a probably longest transmission distribution lines per capita in Australia, probably even in the world, means maintenance cost is quite high. Therefore, we have lots of very long distance lines because electricity is reached everywhere. Because of those trends, we are also starting to develop microgrids. Looking at the fringe of the grids are also developing. We are effectively taking almost renewable energy penetration is becoming probably in very soon may hit 100% rate. Therefore, there are issues as I listed here, and then also some of the conventional power stations are reaching their technical life cycle. There are the balances and then difficulties in terms of stability issues are coming in. And most other issue is that I highlighted here, the cost of energy is probably also the highest, probably in the world even. Definitely in Australia, but probably also in the world, we have the highest energy cost. Because of these aspects, we are effectively witnessing many, many different changes. And then, as we know, all the renewable technologies are all power electronic systems. We are also having other difficulties, especially which will occur soon in EV uptake. When the electrical vehicles comes in, we are not having an additional capacity to be able to supply those demands. Therefore, all the changes in renewable energy sector and then all forces to drastically changing the grid structure. And of course, there are certain measures are taking to reduce those intermittent source related aspects, issues. And we also developed a virtual power plant first time. And then we have the biggest battery, grid scale battery system, Tesla's battery, over 100 megawatt system is also built in South Australia. I guess the big picture wise, lots of power electronics converters, systems, and adapted to these biggest changes. I will also indicate some of the issues which we are facing from the grid viewpoint, outside, apart from the stability issues. This first figure, as you see here, showing the vertical axis is the grid power. These are measured data. One typical value is given for 1 day. Red one is the active power variation, active power demand on a given line. That particular day, we also measured the solar irradiance, just showing that when the power is the direction of the power is effectively in a distribution level, is this one, is simply related to the solar irradiance. Because of the too much PV penetration on the rooftop, therefore we started observing power quality issues. The voltage variation becomes quite large, and therefore different inverters respond to these voltage variations differently because of their original settings over 10 years. Some of the legacy inverters are becoming difficult. Some of the most recent virtual power plant related inverters are reacting well, but they are also remotely controlled. Therefore, customers cannot generate electricity. There are more problems are coming in, and more battery storage aspects also becoming implemented household level. And when you add them all up, there are lots of issues. One of the major issues, which is shown in this slide, the bottom figure, is that many people probably seen a reverse power flow in the distribution system because of the PV uptake. Now we are seeing, I just showed this is a 0 level. Can you see my cursor? Is it moving? Yeah, this is a 0 level here, as you see. I just showed the negative sections. This is a transmission level reverse power flow, not only the distribution level, transmission level, even the power is flowing in the reverse direction because of the too much PV generation in the local area. That's also a significant issues in terms of those tap changing transformers are not functioning well or functioning differently. This is another analysis which we have done in one of the town near Adelaide. Near means about 250 kilometers away. In that area, what we did also, we looked at the section of the grid distribution system. We looked at the impact of the PV penetration. On the left-hand side, it's assumed that the traditional grid means no PV was attached to the same side. As you see here, these heat map or these green light shows that the voltage is within the range defined by the standards. When in the same grid, when we start putting PVs, more PVs are coming in, the red indicates that we are going beyond the voltage range defined by the standards. When we again looked at the same system with a battery storage system, I call it community level battery storage integration, everything becomes normal again. But there are other issues which we also looked at, that in any system, there are when the power flows in a bidirectional way, the losses effectively increases, because in either way, the loss depends on the line transmitted. Loss contribution becomes greater, and effectively the customer pays for this loss in terms of energy. Okay, as I said, the power transformation is already occurring. There are distributed energy resources are becoming quite commonly used. And the most other critical issue is that the loads, electrical loads, are also changing. Or I also call it has already changed. In fact, it's very difficult. Probably I guess the organizers has maybe shared or will share one of the papers which we published. That paper will be available to you to look at it. It's called DC is the Future one. On that paper, I also listed the type of loads used in practice. We can hardly find a load which requires an AC only, except maybe cycloconverters used in mining machineries, large-scale mining machineries. I guess the trend, what I'm trying to say, that because of the renewable aspects, trend is almost DC, and because of the load, also demand is also DC. However, because of these traditional legacy system, we are still converting AC to DC, then DC back to the AC. Therefore, I believe we are in this intermediate or hybrid stage. As I indicated also in this fourth point, there are also electric vehicles will come in. When the electrical vehicles comes in, that's also purely a DC. And of course, more developments as well as some of the research work we are working on, and also looking at using the electric vehicles to use the stored energy, give it back to the grid. And as I tried to highlight at the beginning, because of these long transmission systems, the grid transformation happening, it reduces the reliability. And naturally, because of the long transmission lines, maintenance costs, and then the local generation, it simply increases the energy costs greatly. And I guess the figure pie chart on the right-hand side shows the percentage of these energy costs to highlight that which sections we have to address in the long term. And as I said, that paper has already described some of these aspects. One of the issues with the existing grid transformation is that because of these AC aspects, I won't go through all of them. You can probably have a look at later on. But the major issue is that the existing AC has many, many undesirable features. Even if I just highlight one of them, if you just want to regulate AC, you have to regulate the voltage, magnitude, you have to regulate the frequency, you have to regulate the phase. Opposite to that, if you have a DC, you have only one regulation values. On the left-hand side of this slide, I'm also indicating that some of those intermittent changes and then characteristic features probably very well known. On the right-hand side, it is simply indicating that the future systems, even existing systems, are becoming more and more power electronic systems of different forms. And this table simply summarizes, considering the existing state, the embedded modern generation sources as well as the converter topologies are showing in a block diagram mode, namely solar PV system, wind generation, fuel cell, supercapacitor, flywheel, battery storage system, and EV to grid applications. Converter topologies in the existing AC grid is shown here. As an example, we take the PV, convert it to DC to another DC level, and then give it back to the grid again. Just highlighted the red sections, the AC, but if we have a DC grid as an example, at least these front ends, these AC front ends will disappear. Naturally, the overall energy efficiency will increase greatly. And some of the also structure which we are already experiencing, as I said, probably in South Australia earlier than other places, are that currently we have an AC, DC coexist together. However, the actual utilization of the power, as you see, I highlighted inside this house level, is a DC primarily. Some of the appliances may still have an AC, but there is also converting rectifier front end. It's not necessarily to be AC. Once it's probably modified, it will change it. If we already have a DC transmission line, the renewable sources are also at that level as DC. Okay, where is the wideband devices are coming in? I guess that's what I would like to link that. Since due to the power electronics changes and improvements, I believe, as we also observe that if you are not familiar to the wide bandgap devices, wide bandgap, the silicon-based devices switches about 1.2 electron volt band gap. The wide bandgap devices commonly used ones are gallium nitride and silicon carbides are going up to 3+ levels. Even some of the most advanced ones are also going to about 6 electron volt levels. Some of these devices are already available in the market, and there are many projects around the world, which I also try to find out. We also have some of the projects locally we are looking. Simply utilizing these devices, some of those common features are, the benefit of these devices are that we can achieve a very high frequency and very low losses. High frequency in any converter application means, especially in DC-DC converter, means it's minimizing the inductor size. Inductor size is physically minimized, and then also it doesn't require a freewheeling diodes in the inverter arrangement, and then it doesn't require snubber capacitors. And then another most important one is the DC link electrolytic capacitor is not required. You can use a non-polarized capacitor, much smaller in size. That also affects the lifetime of it. And then overall size shrinks. Another benefit is that their efficiency or losses in the device is relatively constant, not dynamic as in the silicon one, means as you reduce the current, efficiency will go down, and vice versa. And then another issue is that the junction temperature of these devices can go up to over 200, 250 degrees Celsius. It also in turn means that less cooling requirements, the heat sinking requirements can be quite less. And I've listed some of those high efficiency results here. Effectively, these devices, in my view, is becoming almost a similar revolution as we have seen in the thyristor invention. And then later around 1980s, IGBTs come in. I think they are now replaced by the wide bandgap devices. And these are the one I indicated. Some of the effectively figures are shown here that, for instance, the status of these commercial devices are shown here. Even this is probably a year old, this data. There are probably more coming in. As you see, the gallium nitride hemp-based devices about 600 nanosecond at 350 volts. SiC devices, silicon carbide, can be about a single device has a rating this much. Some of the desirable characteristics are listed here in wide bandgap level. They are, as I indicated, higher operating temperatures, faster switching speeds, as indicated, reduces to some of the passive components, but there is a potential aspects of the generation of the electromagnetic interference. Then also has a very higher dVdt, dIdt ratings, which is good things, but it also introduces a potential issues about the sensing. It means if you are going to regulate the current, you have to measure that regulated current at that rate. Therefore, more like the high voltage, high power applications are trying to solve these problems in an integrated module level solutions. And this is also slide is also summarizing that aspects I discussed earlier, silicon-based versus a wide bandgap type of devices. And these charts simply indicates energy gap level, field level, thermal conductivity, melting point, and electron velocity, which is, for instance, related to the high switching frequency. Thermal conductivity and melting is related to the high temperature operation. And energy gap and then electric field is related to the voltage level. as you see, simply silicon carbide and gallium nitride has significant benefits over the conventional silicon-based devices. And then on the right-hand side, this photo is also showing that their physical size can be also smaller. What this means that you can shrink the entire system further, because that becomes critical in some of the applications. The converter power versus switching frequency and application areas are also compared in these figures. As you see here, there is a significant opportunity. Silicon limit is finishing somewhere here, but wide bandgap devices are offering much higher operating frequency as well as the much higher power. Then on the right-hand side, it's also showing the range of applications. And then I think this application doesn't clearly show some of the major ones, like in a distribution and then transmission system level, but they also fit into this area here, mainly high voltage DC level. Physical characteristic numerical values are also given at the bottom table. And this slide is given to you to indicate some of those implemented or commercially available studies. If you look at, for instance, the left-hand side, that's probably I use mostly to indicate it. Medium voltage fast charger was originally this big. Wide bandgap devices is achieved about 10 times size reduction, 4 times the weight reduction. And of course, that in terms is a cheaper installation. Maybe related to this, I also would like to indicate that maybe jumping to the right-hand side, in 2019, and using the wide bandgap devices, and then commercially, people achieved about 60 kilowatt per liter power density using a traction drive. If you just focus on this left side and then right side application, what is happening even in electric vehicle arena, probably those stationary charging stations will disappear. Everything will become an on-board, even including a fast charger on board of the vehicle is going to happen.
Bien, sí, señor. Muy bien.
Hello? Yep. This slide is also showing some of the trends and then also annual growth in the wide bandgap applications. And as you see here, there is a clear trend that it is increasing. I just recently produced one figure, but I didn't have a time to show it here, that I also looked at the publications since 2005. Is a very exponentially increasing publications are occurring in wide bandgap arena, primarily on the application side in different areas, from UPS, motor drives, and wind turbines, and so on. There is a great potential which is already here. Potential, some of the applications, I mentioned some of them, but I will just go through quickly. Some of the perfect wide bandgap device application includes battery chargers in vehicles, battery storage systems, PV systems, renewable energy technologies, including wind turbines, motor drives, and then power supply applications. This is also a project which we are currently working on it using this topology, this type of devices. I guess the main benefit is that because of the higher power density can be achieved, as well as this device can operate at very high temperature, the microinverters will become possible to integrate as a part of the panel, or DC-DC converter can become a part of the panel. Another unique feature which we are using in our research project, if you are interested, and I can talk about that more, we are also trying to develop a new panel structure. Simply, panel can be divided into sections, including a number of cells, equal cells. We can simply reconfigure those cells in the case of shading. This is also possible using this type of devices. The reason is that the gallium nitride devices inherently a normally on device. It means if everything is normal, the system can be connected in series. If something goes wrong, you can simply use other parallel switch arrangements across any panel level. You can reconfigure the string arrangements to another form and then develop a converter to step up or down when it's needed. Our estimation is that we can easily achieve 5 to 10% additional energy yield by doing this type of study. And EV chargers, I think I mentioned some of them, as I indicated, onboard chargers will occur, or already there are some studies done. Therefore, the offboard activity will disappear. And this table also showing that silicon carbide or gallium nitride based studies can achieve the efficiency range as illustrated here. And other applications will come in the power system level is since the reduction of the or increasing power density is possible both volumetric as well as the gravimetric level. And then transformerless, in fact, there is a transformer if you want isolation, but this transformer can be a high frequency transformer. Therefore, size will shrink. Effectively, the substations are likely to be replaced by the wide bandgap device-based converter topologies, configurations. This is one of the implemented ones. Then I simply also summarize here, considering, for instance, if you replace the existing transformers with the solid state transformer versions, where the isolation is achieved by, again, with the high frequency transformer, we can achieve all these benefits from the smaller volume to improve the efficiency. Bidirectional power flow is possible, can improve the power quality and so on. If you have a DC grid, just earlier discussion, we will not have effectively ACs. Therefore, we will have additional benefit in terms of more control. Of course, reactive power control will disappear. Power flow is always bidirectional possible. And then voltage regulation is much greater using this type of arrangement. Here is another large-scale utility-scale application is shown here. This is called transformerless intelligent power substation, TIPS. This is an AC version. It looks like this. And then if we have a DC grid, and then we simply remove those AC, DC, DC, AC front ends. And here is another application, wide bandgap device used motor control applications. As you see, similar benefit will also come. Conclusion, as I indicated, wide bandgap devices are coming. They have a great potential to revolutionize the power electronics applications, and then which will also in turn affect the overall power system components. And one application just came up is that now you can find even commercial circuit breakers using wide bandgap devices. Because of this modularized structure, we can also control the current. We can regulate the current. We can control the voltage. We can also use as a protection device. It means one circuit breaker replaces the conventional circuit topology, like fuse will disappear. They will also allow onboard high power DC charging of EVs, and then also vehicle to vehicle conversion will be easy. Vehicle to grid power transfer will be easier. And our prediction is that they are likely to drive this grid transformation in a much greater scale, and then which will probably replace the AC to DC entirely. I will stop here and thank you.
Thank you very, very much for your very interesting presentation. And now I am sure we will have many questions. I am looking to the chat, and there is one question here. Is it technically correct to call TIPS as the transformers less topology, as eventually it use high frequency transformers?
This one?
Is it technically correct to call TIPS as transformer-less topology, as eventually it uses high frequency?
Yeah, well, I use the existing literature. I didn't change myself. Of course, people call it transformers. It is with transformer, but it's with the high frequency transformer. That's I guess transformer is definitely needed in high voltage applications because you need isolation. Yeah, this is not a terminology I found it. I found it in the literature.
Okay, thank you very much.
The reference probably is given in my paper. I think I don't recall here, but these are the ones I produced. But yeah.
You can share your paper. Yes, you already shared, Nicolas.
I did share. I send it together with the presentation.
Exactly.
We can the mails, but I will share it here in the chat.
Yeah, that's great. That could be because it's a very comprehensive description of all the issues treated today. Luis, before go to other questions, if you want to make some comments and some reactions to the presentation, Luis Moray.
Yes, of course. Well, first of all, I think the presentation was very clear, so I want to thank Professor Nesimi for that. And very interesting is the future of power electronics. And I have a question. I mean, one of the problems, you mentioned something about protection, but one of the problems that have a DC system is about the arc, the electric arc. Do you have any opinion of that? Because you mentioned that we have so far circuit breakers implemented with power electronics, but what's the rating of these circuit breakers, and what's your opinion about protection in DC power systems?
I guess that probably depends on the technology which will come. I will just show it here. I guess the one issue is probably these figures, dV/dt, di/dt ratios are at this scale. You can, of course, connect them in series or in parallel to increase these ratings. The key issue is, as I indicated, the measurement aspects. That's why, as shown here, people start modularizing it. Physical size, I did also show here, these are all limited to the existing commercially available device, which is outside my expertise. I would like to see that happening. If you look at these figures, these are borrowed from some of the Subhashish's, one of Subhashish, I think he was with earlier with the Wisconsin. I know him. And they developed sort of 20, 30 kilovolt sort of level so far.
Okay.
I guess when these devices becomes bigger, higher voltage, higher power becomes available, that will not be any problem. And then I also listened one of the tutorials some years ago that some of these wide bandgap device manufacturers are also looking for a specific niche applications. They were mainly looking at the motor drive applications originally. Therefore, if they start sort of looking at the distribution transmission level applications, probably that problem will be solved, I believe. And as I also said, about 6 EV electron volt level devices will come in. Therefore, that will extend the range further.
Okay, thank you very much.
Thank you. There is another comment here, or a question about the major challenges that your team face while dealing with these wide bandgap devices.
Major challenge from the application viewpoint?
Yep.
Based on your experience in your team, yes.
I think I tried to summarize some of them. The major, very biggest challenge I find personally is the measurement of the current. When you go to high frequency, how will you measure the current? The best way to measure the current at the high bandwidth is not using the Hall sensor or this and that, is the resistor. Right? Shunt resistor is the best way to measure if you are after very high frequency current measurement. But when you do that, and then isolation disappears, and you need to isolate it. As well as the high frequency is the EMI becomes an issue, and then also leakage inductance becomes an issue, because not only therefore I think the application will go to a modular levels, means the actual manufacturing level. As a power electronic person, we will not be able to use them as an individual. Probably it will come in as a package where the measurement is done, control is done, protection is everything, driver is done. EMI issues are addressed already, which is somehow shifting the issues to the manufacturing level, not to us.
Okay.
Thank you.
Okay. I wonder if you can comment, Nesimi, about a connection of your description with circular economy challenges worldwide, because you comment, for example, that you need less materials. So dematerialization could be one of the issues in circular economy, can be very aligned with this type of trends. But if you can comment a little bit more, because all the energy transformation and sustainable development needs to work on these circular economy issues, and perhaps you have some opinion about recycling, about reuse, etc.
Recycling, I guess I can make some comments if I understood correctly. I was giving some lectures in the previous years about electric vehicles or vehicles in general. During that time, I indicated that hybrid vehicle we used to have some years ago, we still have it, is the transition stage. In fact, after that, I said target is to go to EV. I think almost I have the similar sort of view here, that that's why I give or emphasize the South Australia case more, because we are already in the middle of the larger scale transformation, going more renewable aspects. Every household has almost EVs, PVs now. Therefore, this transition is the hybrid level is already happening. My view is the target, it will be a DC. It will be it will not be an instant changes. Probably I can show you. I had some slide here, which is this one here. This is also given in the paper. This is how it started. Where the green is the load center. Some conventional generators in the first 1880s, when the first electricities started distributed, Edison distributed in DC. We had a generator next to the load center. Later, 1900, it happened this way. Currently, we are here, where we have more AC still. I think near future, that's my prediction, around 2030s, probably also these predictions depends on where you live in the world, of course, will become more DC dominant. We are already more DC dominant already. And that's what I was talking, that the fringe of the grids probably will disappear. Rather than having a long transmission line everywhere, we can, some of those towns, I was mentioning earlier that town itself, we calculated that in one of the town analysis. Remember heat map area? We analyzed that entire town, that we know the power consumption. If you use the entire roof spaces in that town, you can generate 2 or 3 times more energy than the consumption. Right? I think these will start happening. Microgrids will happen. Autonomous microgrids will come gradually. In terms of recycling, I think that will effectively similar to the power station. When the power station disappeared, which happened here in South Australia, and then recycling will happen naturally. But we started thinking about recycling the batteries now. What to do? Because that's a major. Some major projects are going to happen. How to recover those batteries? Maybe look at the second life first, like electric vehicle batteries will become a second life in the stationary application, and stationary one will become maybe third life, refurbishing again. And after that, it will be completely recycled and materials will be separated, lithium plus, maybe others.
Okay.
And 2050, I sort of, my vision is that probably we will have more where we started.
Yes, you don't see any big advantage in interconnections for your future.
I don't think so. I talk about these power. Remember, the interconnection was needed because we have to go to the high voltage to reduce the losses. Now we locally produce this, therefore losses also happens when this flows this way. And plus, I can locally generate it. Especially in Australia, all the houses are single story, not apartment. Therefore, I consider that even in the near future, some of the big towns, big cities, industrial sites may still need some larger scale generation. In fact, I indicated here, if you recall the earlier figure, this is probably how it will look like. Generation will still be done AC, but we will have an AC-DC conversion here at this point. At this point here. And done, because the rest is DC.
Yes, this is also the case in Chile, where we are a rich country based on renewables, like Australia, especially solar and wind. So it makes sense in this type of landscapes to see this type of future. Especially
if it's an off, say, fringe of the grid, long distance. Yes. Why do you take the transmission there? And then also plus environmental factors. I think your cases, you have earthquake, we have weather.
All right. Fact, earthquakes are.
Yeah, one of the blackout happened here due to the combination of effects, but also weather contributed that.
There is a final comment here from Osvaldo. In some way, he come back to the comment of Professor Luis Moran, but if you can comment, the size of the HVDC circuit breakers is very large. I have seen in China a 500 kV, 20 kiloamperes DC circuit breaker that was at least 200 times larger than the equivalent AC circuit breaker. If you can comment on that, please.
Well, I mean, correct. I agree. I think my probably comment will be this is a very overview of it. I think I indicated here, for instance, this is you see this purple one here, an HVDC line. Maybe some will stay, right? Some section may stay. In China case, China is a very energy hungry country. Therefore, they use the Western energy generations to transmit to the eastern part where the industrial sites are. They develop those things. But my other view I have is also microgrids are the way to go, because you can manage easily, you can regulate easily. Then also it will give a little bit more redundancy, because if you have multiple microgrids, if one fails, the rest will keep operating. But other existing conventional system is very prone to external influences. Even if someone attacks that line, for instance, it's all gone. Therefore, system security will come in. Cyber security will come in an interconnected system. Rather, if you have a localized, dedicated local generation, which is possible now, more efficient. That's what I'm trying to say. It's yes. Even the diesel generators may be used a little bit limited scale. However, diesel generator will have an inverter output to operate at the highest efficiency all the time, which Australia has some areas. Lots of Aborigine sites has a diesel generator powered. And then mining one is also impact, which we are working on it, mainly the pollution, especially in underground mining. The more tendency is going towards the more electrified mines. My point is, wherever you electrified, it's a power electronics, and then renewable energy source. That has to happen.
Great, thank you very, very much. I think, Luis, we are ready if we can finish this, and thank you again for your to stay with us until this late in the night for you, and
It's
I hope to see a future of cooperation between our groups. And please, Luis, if you want to close the seminar, please.
Yes, well, thank you very much, Nesimi, for your presentation. Was very, very interesting. Is the future of power electronics and where the power system will go in the future. So it was very interesting, and also I would like to thank all the audience that are present today. Was a challenge for us that work in research to continue to study these new systems. And well, again, thank you very much for your presentation, and I hope to see you soon in Chile.
Yes, I will. I'm looking forward to.
Okay.
Once we have all our vaccinations done, I guess.
Yes. And this pandemic passed. Okay. Thank you very much. Thank you. Gracias,
Thank you.
Rodrigo, por todo. Muy buen seminario.
Thank you. Have a good day.
You too.
Bye. Gracias, Nicolás, por el
Nesimi.
soporte. Que esté bien.
Okay.
Chao.
Nos vemos. Gracias. Chao.
Gracias a todos so much. Thanks.
Bye.